So our next pair of speakers is Bailey and Andrew from Concordia College. Go ahead.
Thank you. Just share my screen here. There's that.
Great. So I'm Bailey Klause.
And I'm Andrew Middendorf. We are from Concordia College in Moorhead, Minnesota. And today we're going to be talking about our research that we conducted over the summer of 2019 on the investigation of the magnetic properties of aluminum, nickel, and chromium doped goethite. This research was facilitated by Dr. Thelma Burko with assistance from Dr. Graham Wiley. So just kind of an overview. Goethite is an iron oxide that is the most thermodynamically stable iron oxyhydroxide at room temperature. And then hematite is another iron oxide that'll come up. And that is important because hematite can be formed from the same starting materials of goethite, just at different temperatures and pH values. Our research focused on how we could dope goethite with three different cations. These were aluminum, nickel, and chromium. And we picked these three cations, aluminum first because it is one of the most studied different dopings into goethite, and so it has a lot of published literature on it. Nickel because it has a +2 valence and it also had a similar method of preparation as the aluminum samples. And then chromium because it has a +3 valence, and then it has a similar method of preparation as the aluminum samples as well. Goethite is significant, especially in its doped form, because it is very commonly found in nature and in laboratory practice. And it has a lot of uses in things such as pigments, biomedical applications, and electronic applications. In our research, we synthesized 3 different batches of goethite samples. First, an aluminum-only doped sample, and then a aluminum and nickel doped sample, and then an aluminum and chromium doped sample. So we're going to talk a little bit about how we prepared these different samples. The method of preparation for all the samples was an adaptation of that found in Shortman and Cornell's book, Iron Oxides in Laboratory Preparation and Characterization. And the reason why it was an adaptation was we took the initial method and we scaled it down to about 1/10 of its original size. And we also added an extra target molar percent of 24%. All the different labeling in this presentation is going to be the target molar percent that we were going for with the different substitutions. This method boiled down to mixing solutions of iron 3 nitrate, aluminum nitrate, and potassium hydroxide together, and then dividing them up among centrifuge tubes. These centrifuge tubes were then aged in an oven at 70 degrees Celsius for 14 days, and you can see the end product here on the right. One thing to note here is the spectrum of color that you see. On the left-hand side, you see a little bit more of a yellowish color. That typically indicates to us that goethite was being formed. But if you look on the right-hand side there, you see that little bit of reddish-orange color. That could indicate to us that another iron oxide was being formed. This could be that hematite that I mentioned earlier. For the aluminum and nickel samples, this was very similar to the way we prepared the aluminum samples. The only difference being we added a nickel chloride solution into our array of solutions that we mixed. The samples were again divided among centrifuge tubes and aged in an oven at 70 degrees Celsius for 11 days this time. And if you look at the image on the right there of the samples at day 11, you can see they're all kind of that yellowish color, indicating that goethite was probably the primary phase being formed here. For the aluminum and chromium samples, it was very similar to the aluminum and nickel sample preparation method, the difference being instead of nickel chloride being used, we used chromium nitrate. Again, the solutions were mixed and divided among centrifuge tubes and placed in the oven at 70 degrees Celsius, this time though for 132 days. One thing to note with the aluminum, nickel, and the aluminum chromium samples is we kept a 4% aluminum constant across the board there instead of ranging the aluminum and the chromium and the nickel. And so we kept that 4% aluminum and then we added chromium as we went. And if you look at the samples on the right there, you can see the first two are a little bit yellowish in color, but then we get this purple hue kind of showing up. And that's because the chromium kind of adds a purplish color to the sample. So the first technique that we used to evaluate our samples was Bar spectroscopy. And this is important when you're evaluating iron oxides as it provides a lot of magnetic properties that can be used to identify and characterize the different samples. And Bar spectroscopy, for those of you who aren't familiar with it, it's performed by moving a gamma ray emitting source. For iron oxides, this is typically cobalt-57. These gamma rays can then interact with the nucleus of our sample or absorber, and that can give us information to describe the nuclear environment of the sample being tested. The spectra that this will create is going to be a count of the gamma rays hitting the detector behind this sample or absorber, and then that will be plotted against the velocity of the source. The main factors that this will provide for us is the maximum hyperfine field values and then the relative percentage of the sample that is reported.
All right, so here we can see the spectra that we got from our aluminum only samples. And you can see on the top sample, we have this nice like ordered sextet of peaks, and that is because goethite is magnetically ordered. And then once you start to see more of a doublet character, that is something that is not magnetically ordered and indicates to us that it has a small particle size. So you can see with our samples, once we start to increase the substitution of aluminum, we get more and more of this broadening and collapse of the peaks as we go down. And that is caused by defects in our sample. So, and these defects could be things like substitution or vacancies, but we can't tell which is happening based on this technique alone. And you can see that all the way down to the 24% aluminum samples that we're just making mainly this doublet phase that just has really, really fine particle size and is probably super paramagnetic. And then here, these are the parameters we get from the spectra. And the main things to look at here are the hyperfine fields. So for a well-crystallized stoichiometric goethite, you expect to see a hyperfine field of around 38.1 Tesla. And then for hematite, that's around 51.8 Tesla. If you look here at the aluminum samples, or the 0% aluminum sample, it's 37 Tesla, which is pretty much tells us that we're making goethite and it might not be super well crystallized or stoichiometric. And once we start to increase the aluminum substitution in our samples, then we start to make more and more of these non-goethite phases. And once you get all the way down to the 24% aluminum sample, we aren't making any goethite at all. We're just making hematite and then mostly this super paramagnetic phase, which again is just saying that basically when we increase the amount of aluminum in the system, that we are decreasing the particle size. And then here, these are the spectra that we collected from our nickel samples, aluminum nickel samples. And here you don't really see very much of that broadening effect happening. And that basically is telling us that there really aren't that many defects in these samples. And the nickel is not having much of an effect. You can see a little bit of a doublet arising in that 4% aluminum, 20% nickel sample, but it's not super pronounced. And then here, these are the parameters from the nickel samples. It basically agrees, like once we start introducing the nickel, we're really just making mainly goethite, a little bit of the super paramagnetic phase in the 4%, 20% sample. And then here, these are the spectra that we collected from our chromium samples. So here you can see way more of this effect of the chromium. You can see that once we start to increase the chromium, these peaks continue to broaden and collapse, and you can kind of see almost step by step how that turns from a sextet more into a doublet. And once again, this broadening and just kind of collapse of the peaks is due to the defects in the sample. And that doublet there at the last sample is, once again, because we're making more and more of a phase with small particle size. Okay, and then these are the parameters from the chromium. And you can see here, if you look at the 4% aluminum, 4% chromium sample, our hyperfine field has decreased all the way down to 34 Tesla, which is telling us that either we're not making very stoichiometric goethite or the particle size is decreasing. And then all the way down to this 4% aluminum, 20% chromium, it's decreased all the way down to 28.4 Tesla, which probably is saying that we're making, like I said, defect heavy goethite or small goethite. And then also you can see that with the increasing chromium, we are making more and more of these non-goethite phases. One important thing to note here is that if you remember back to the 24% chromium samples, or aluminum samples, sorry, we didn't have any goethite, and here we do still have some goethite, which means that maybe the chromium does not affect the particle size as much as aluminum does.
So the other test that we used to kind of characterize our samples was a super quantum interference device magnetometry, or SQUID magnetometry. And this works by identifying the Néel temperature of our samples. And the Néel temperature is where the magnetization in the sample goes to 0. For goethite, this Néel temperature is around 393 Kelvin. So if you look at our samples on the right there, you can see with the 0% aluminum sample, we get this magnetization to go to 0 around about 370 Kelvin. This indicates to us that we had goethite present, but it probably wasn't the purest goethite. And then as we increase defects, we expect this Néel temperature to decrease. So if we look at the 4% aluminum, 20% nickel samples, we see a slight shift down to about 350 Kelvin. And this indicates to us that there were some more defects present, but not what we'd really expect. With 20% nickel substitution, we'd probably expect a little bit more. So we're probably not getting complete substitution there. And then with the 24% aluminum sample, we see that shift all the way down to about 290 Kelvin. This could be caused by a lot of defects or small particle sizes there, indicating to us that maybe substitution was occurring. So just to kind of summarize what we talked about, in our research, we studied how goethite could be doped with 3 different metal cations. These were aluminum, nickel, and chromium. Aluminum was chosen because there was a lot of historical papers on it and a lot of evidence showing that it could be done. Nickel and chromium were chosen for their similar synthesis method and the fact that they had 2 different valences that we could test. Aluminum substitution was likely to have been successful, as this was indicated by the increasing amount of defects that were shown as we increased the amount of target substitution that we were going for. Aluminum and nickel substitution, however, was less likely to have occurred, as the hyperfine field values and near Néel temperatures indicated very little defects as we increased the amount of target molar percent dopage. And then the aluminum and chromium samples seem to have been successful to be doped, as they had a major effect on the amount of defects that we saw in the samples as we increased the amount of target substitution. So just some acknowledgements. We'd like to thank Dr. Thelma for facilitating this research, Dr. Graham Wiley for his help with the chemical aspects of the research, the NASA Minnesota Space Grant Consortium for helping provide funding for our research, the Institute of Rock Magnetism for allowing us to use their equipment, such as the squid magnetometer, to help test our samples, and then the Concordia College Undergraduate Research Scholarship and Creative Activity, or ERSCA, for helping support our research.
Okay, thank you. So I will lead off with the standard question, and that is, how might NASA be interested in either the results or in people being able to do this kind of experimentation?
Yeah, I think a pretty obvious one for NASA is that iron oxides are found on Mars, and they used Bar Spectroscopy on the Mars rover. And then other less direct applications would be, or reasons would be the applications it has, and then just its prevalence in like soils and around the Earth.
Okay, let me just follow that up with, how were the timings chosen? I mean, 132 days, did you just report on that sample when you did all parts of timing, or there was a good reason for stopping at 132 days?
We found in the literature that each of the samples had kind of a timeline laid out in the literature for their own methods. The aluminum said around 14 days, the nickel said around 11 to 12 days, and then the chromium had said like 130 to 150 days of aging. So that's kind of how we determined it.
Okay, that's great. Questions from other people who are listening in here?
Maybe you said this and I missed it, but is your goal, are you looking for certain magnetic properties, or are you trying to find a way to manufacture very pure goethite for study?
Yeah,
So
we
you can go.
We use the magnetic properties to identify and characterize our samples. So we're just trying to see what happens to like the characteristics of the sample once we start introducing more and more of these cations in the system.
Thank you.
Okay, thank you. Watching the time, I think we probably should push on. Thank you.